binaries, which is the topic of this talk. It's not changing. There it is.
Can you just get back to your title slide? The recording.
Recording.
Just so they can see the front page.
Oh, okay. 1, 2, 3, 4. There it is. So, as a little background, we expect to find a supermassive black hole in the center of every galaxy in the universe. For some galaxies, another phenomenon is called an active galactic nuclei, which is when these supermassive black holes start accreting gas at such a high rates that start emitting huge amounts of radiation into space. So we can see them from very far away distances. And another phenomenon which is very common in the universe are galaxy mergers, which were actually very common in the early universe. And we expect supermassive black hole binaries to be formed from these mergers. So the way they form is that imagine you have one supermassive black hole for each galaxy. As they are merging, they will start experiencing dynamical friction from all the chaotic stellar environment of the two merging galaxies. So they will lose almost all the momentum, and they will eventually meet at the common center of mass into tight orbitals. Also, the movement of the black holes can make gas flow from both the galaxies into the common center of mass, and that can form a circumbinary disk around the two black holes, which can also trigger nuclear activity in the galaxy. By nuclear activity, I mean AGNs. So the difference of these AGNs is that the movement of the two black holes can perturb the gas in the circumbinary disk, and that can cause a variable accretion rate and a periodic light curve, which will be tied to the period of the two black holes. So I found this great illustration. This great illustration from Kelly from 2018, which shows what we should expect from these systems. So we have, of course, the two black holes. We have a circumprimary and a circumsecondary disk around each individual black hole. We also have, of course, the circumbinary disk I mentioned. We have this zone called the gap or the cavity, where you have particles that every orbit is unstable, so they either can get kicked out of the system or they fall into the black holes. And we have also these gas streams which feed gas from the circumbinary disk into the circumsingle disk. So we have two sources of variability in this case. We can have intrinsic variability, which is the hydrodynamic variability, which is when each individual component accretes more than the other by different phenomena, whatever. And we also can have Doppler variability because this black hole will be orbiting each other at very high velocities. So as they're moving, as they're approaching us, the light will be blue shifted, and if they receive from us, the light is going to be red shifted, and it's going to be dimmer. So in this animation from Dan Hill and Jorge Cuadra from 2015, they simulate a binary stellar system. I don't remember the name. They use 2 million particles, and here you have all the elements I mentioned. You have the circumbinary disk, you have these gas streams, the circumsingle disks, and also you see this this density waves that propagate outwards from the binary, which are the ones we expect to see. So in order to detect this supermassive black hole system, we have to take into account that they are way too far away to be able to resolve the disk. So the only way of detecting them is by indirect methods. Like in my case, I studied the periodic variability of the light curves. In this case, you have a time series of a quasar of AGN, and you can feed a model. In this case, that will output you properties of the binaries, like, for example, the mass ratio, the eccentricity, or whatever. We also have another methods, in this case, multi-epoch spectroscopy, which consists of taking spectrum of an emission line of these systems and fitting models that can allow you to infer properties of the binary system. In this case, this paper from 2025, they observed the same magnesium 2 emission line from the quasar at different times, and they use a model that can output the mass ratio of black holes and also the positions of the black holes in this case, which is a very useful method actually. And the third method is from gravitational waves, which will become relevant in the future when the VISA project becomes operational. So as previous studies, we have the study from Orazio in 2024, which he modeled different mass accretion rates for different configurations. In this case, they had a whole range of eccentricities and the direction of the circumbinary disk. For this case, I'm showing you prograde, a binary system with a prograde disk. And the first thing you notice is that for low eccentricities, you have also a low mass accretion rate comparing to high eccentricities. But also you have the one component, in this case, the secondary component, which is mercantile, accretes much more than the other one. For even high eccentricities, you start noticing that the accretion becomes more sharp. You have these very distinct sharp peaks, which coincide, which are aligned with the periastron of both components. But also you start seeing something like the mass accretion rate of both components start becoming roughly the same. They also model retrograde disks. In this case, the accretion is much more stable and predictable, and the mass accretion rate of each component is the same, basically. So, the objective of this work, we aim to model a circumbinary disk around a supermassive black hole system. We also want to use MC-FOSS to model radiative transfer and study the effects of the radiation on the mass accretion rate. And as a hypothesis, we expect the mass accretion rate to be reduced by the effects of radiation, because as the gas start becoming close to black holes, it start emitting more radiation that can heat up the gas and repel it. So here we have a very early work in progress stage, I think. So we experimented with a lot of configuration for the initial disk parameters, but eventually we settled down on using the same parameters as Salt Router used in 2024, which consisted on a 0.1 solar mass disk around a single 1 solar mass star. So we started adding parameters, we started modifying things, and of course we added a binary system instead of a single star. And I don't know if you can see it, but here are the two components. A little smaller to see, especially because the disk is 100 astronomical units in radius. So we made another model, which is smaller. It's only 20 astronomical units, but you can resolve the two components of the system. I also scaled the mass of the disk, so the density will stay roughly the same. And an important thing here is that we haven't enabled accretion luminosity yet. We are only using stellar sources. So here I show you an animation of two disks. One is with radiative transfer enabled, and the other one is with without radiative transfer, using beta cooling, and using the same parameters as Router used as well. So beta, I think it was something like 15.
Oh, is that with MC-FOSS?
This one is with MC-FOSS. Yeah. So here I show you some very preliminary results. In the first case, we have beta cooling, where you see this periodic variation of the mass accretion rate, and a more steady variation for the secondary component. And also you can see that the mass accretion rate scales increases linearly with time. now I show you radiative transfer. You see a more noisy mass accretion rate shape. Also the like the growth of the two black holes, sorry, the two stars changes shape considerably. So, well, as I mentioned, this is very early stages. We started this project like 2 months ago, so we haven't got much time to work and refine parameters. Another thing, all the examples you saw were for stars. Basically, they are not black holes yet; they are just solar mass stars. So things we want to try now is to replace the dust opacity with electron scattering, which is something you can expect from the vicinity of black hole systems. We also, of course, want to replace the stars by actual black holes, turning off the radiation from the stars and enable accretion luminosity. And enable viscous heating in the disks. So because we're in very early stages, we appreciate any comment or suggestion from the community. So that's my presentation. Thank you.
I have some time for questions. No questions from PhD students.
Yep.
First, okay, and then François.
Just by viscosity, what do you mean exactly in that context? Like there is the heating already, like from the, depending on the equation of state, you can get the heating from viscosity that you put in the simulation. So
yeah, it means that for the current simulation I showed you, that have viscosity turned off by default, because when you use MC-FOST, sorry, in the initial parameters we use from router, in the MC-FOST example, this viscosity was, sorry, the heating of the disk by shocks was turned off. I think that's the answer, sorry.
So basically you don't have PD1. That's the thing.
what's along that term?
Yeah, so
Although in the viscous heating is not turned off in phantom, but you can get the PDB work and shock heating into MC-FOST as an additional.
I'm sorry, I don't hear you.
no, it's not that question. Just commenting the fact that when you're running the thing, you can either decide to activate or deactivate PDB
Oh yeah,
which is an extra term for the energy.
Yes, so it's going to turn off. It's only not included in the hydro steps, but it's included. It can be included in MC-FOST.
okay. Yes.
Yeah. So it's a little bit subtle because so we switch it off in the hydro, but we give it to the radiative transfer, and so it acts as a heating source in MC-FOST, not in phantom.
You have two parameters actually. You have one in MC-FOST, which is PVB, and the other one in phantom, which is also PVB heating and shock and capture.
But it's important that you don't double count.
Yeah.
So,
no, that's important.
François and then Beck.
So the next question here. So for the radiative transfer part, do you expect you'll have to deal with relativistic effects to propagate the energy?
Oh,
Because photons might not propagate in a straight line, for example.
yeah.
We should repeat the question. So the question is basically if there are some relativistic effects related to, I mean, how the radiation will propagate close to the black holes.
Yeah, we actually thought about that. We are not simulating the inner parts of the black hole, like the very close vicinity. So instead, we use very large sync radii for the two black holes. So for now, we don't count the relativistic effects. It's a thing we will plan to use in the future, but as I mentioned, I've been only working on this project for like less than 2 months. But we will do it.
Okay.
So my question was going to be about the sync radii. So like I could see in your movie that there were no certain stellar disks, right? So I could see that you're already using a larger one. But when you're looking at the variability, surely you would have to resolve or at least try to resolve the disks that form. So is that what you're going to do in the future? Or are you, when you do the simulation, you just said, actually, it might be better if we don't resolve the disks because of the GR effects? Like, what are you going to do about that?
Well, we are currently limited by speed, basically. So we try to make this as fast as possible for the presentation. So we use a low particle count, and that explains why you don't see like many detail in the very inner parts. I mean, you see a circumprimary disk, but then it just fades. But yeah, we don't have like enough resolution in this part yet to be able to resolve little of this around.
Is this a good base for APR? That's the point, right?
Yeah, it is actually. But this uses MC-FOSS, so.
That's okay. I mean, we're going to visit this later.
Thank you.
Can I ask a follow-up question?
Yeah, go ahead.
A separate question.
Yeah.
Are you going to consider whether the binary is misaligned to the disk? I mean, given the formation pathway that you have for this binary system, misaligned systems are like quite motivating. So, and that's going to change the accretion variability that you get and the disk structure that you get. Are you going to consider it as well?
We could. One of the things we also plan to do in the future is to explore the parameter space as well. So for this simulation I just showed you, we're using a fixed eccentricity of 0.2 only. So it's a very circular orbit, basically. But we plan to use more, to explore more a whole range of eccentricities and inclinations and everything. Yeah, for now, it's just it.
Time for one last question, Daniel.
More just a comment. There's an incredible opportunity here for the MC-FOSS with black hole disks. There's a lot of problems in black hole disks that no one has ever done the live radiative transfer. So I talked to Christoph about both things many times. Like we want electron scattering, we want, well, which Christoph said it's just large dust, basically, because it's like a constant opacity. So you can just take very large dust grains. It's like equivalent to just having a constant opacity in your disk. And so there should be some easy analogy we could make. But then as Beck said, if you start talking about shadowing by tearing warps and things, you're opening up huge fields where nobody's done any simulations.
But that involves heavy development at the MC-FOSS level, or you think it's portable to black holes?
Okay, so it depends what you mean by electron scattering. If you mean real scattering of electrons, like where they bounce around in different directions, this needs some work.
Just Thompson scattering.
But if we want just an opacity, which is constant, and we're prepared to treat it like an absorption and emission opacity, which is slightly wrong, but it's a good approximation to start with, then it's probably easy.
Okay, excellent. So Jose is going to be 1 week after the workshop here at IPAC.
Yeah.
So we can discuss this later. So thanks again, Jose.